Differential equations. We're in section 2.1, day 2. And let's just look at the notes here. It says we divided ordinary differential equations into two types, linear and nonlinear. An ordinary differential equation in which the independent variable does not appear is said to be autonomous. So what does an autonomous differential equation look like? Well, your dependent variable y, you only will have y, powers of y, and so forth in that differential equation. Today, we're really looking at autonomous differential equations. If the independent variable does appear, generally it's an x, then it's called non-autonomous. So, like I said, we're going to be looking at autonomous equations where if we have a dy dx, we only will see a y on that right-hand side. We will create phase portraits. And you're going to see that in just a moment. We're going to make a vertical line and determine points that are attractors, repellers, and points that are considered something called semi-stable. Here's what you do. You find critical points. This is very much like what you did in BC Calc. You set your differential equation equal to 0. You find out what y values will lead us to have 0. You create a vertical line, like a number line, and you do testing much like you did in BC Calc. So you'll test intervals, find out whether your derivative is positive or negative. That is, you're going to be able to know whether your y is increasing or decreasing. A point is an attractor when both arrows point toward it. A point is a repeller. It's considered unstable, asymptotically unstable, when both arrows point away from it. So attractors will be called asymptotically stable. Repellers are asymptotically unstable. And then, of course, you can have an arrow pointing in different directions. That's what we would call semi-stable. And then you can sketch typical solution curves. So let's just jump in immediately and see what can happen here. So this is going to look so much like what we have done in the past. We can very quickly set our differential equation, our dp dt, equal to 0. Using the zero product property, we'll have p equals 0. Here, 4 minus 2p equals 0. I think it only will take you a moment to either solve by adding a 2p to both sides and dividing by 2, or just solving by what we call inspection. And you'll have two critical numbers, p equals 0, p equals 2. So what you're going to do is you're going to make a vertical number line. Now, last year in BC Calc, we generally would make a horizontal number line, but that's fine. This is an autonomous situation. P is as if it were a y right here. So maybe we could test p equals 3. Down here, maybe we could test p equals 1. Over here, we could test p equals -1. And guys, if you plug in a 3 right in here, you're going to see that you'd have a 3 times 4 minus 2 times 3. 2 times 3 is 6. 4 minus 6 is -2. Your dp dt here is negative. And what does that mean? It tells us p is decreasing here. So what you can do is just show a big arrow like this, and I'm making a different color to really make it stand out. It means as we go left to right on our independent axis, our t-axis here, our curve goes down. It's decreasing. Likewise, if we were to test p equals 1, I think you can see very quickly you'd get a 1, and here's a 4 minus 2 times 1. That's positive. This means p is increasing. Well, we could draw a big arrow and show that our function would be going up as we move left to right. Then finally, as we plug in p equals -1, well, it's only going to take you a moment to see what's going to happen here. You get -1, and here's 4 minus 2 times -1. A negative times a negative is a positive. So you'll have something positive in the parentheses times something negative. What does that really lead us to? A negative derivative. P is decreasing. What we're going to see is our curve is going down as we go left to right. So that is our phase portrait, but let's sketch a possible family of solution curves. Here's what we could get. Obviously, we can see over here at 2, if we were to plug that in, it's almost like looking at a slope field. You can see if we plugged in a 2, you would have a 0 for your derivative, wouldn't you? If you plugged in a 0, same thing, we'd get this. So this is where these asymptotes can be coming into play. Now, if we're above p equals 2, you can see that our curve is going to be coming down. So I'm going to change colors here. And what could that look like? Well, it could look like so many different things, but I'm going to draw it something like so. Our curve is decreasing, and it's getting closer and closer to y equals 2, in which case we'd have a tangent line slope of 0. Now here it's going to be interesting. Our curve is going to be increasing between 0 and 2. And you can think, well, how in the world can we get that? Well, maybe we'd have something that would look like so. So at p equals 2, you saw these arrows pointing towards each other. We have what's called an attractor at p equals 2. This is known as asymptotically stable. So our curves, our family of curves, would be drawn to that. By way of comparison, at 0, you could see they're being pushed away. So, at p equals 0, we've got a repeller. And this would be known as asymptotically unstable. Well, you can see why. We're going to, below p equals 0, it's going to be decreasing. So it's going to look perhaps something like this. So as we go left to right, from p equals 0, those curves are pulling away from each other. They're repelling each other. So that's really what's happening. So, in terms of being an attractor or a repeller, it's as we move left to right with our independent variable. So that's really example 1. Let's see if we could quickly take a look at example 2. For example 2, I do think it only takes a moment to find a critical point, and it's going to be pretty evident that, there's only one critical number here. It's y equals 1. And at y equals 1, well, we can have our 1 right here. We could test y equals 2. We could test y equals 0. But at the end of the day, guys, look at this. Everything's going to be positive. So that your y curve is going to be positive here. So we'll have our going left to right. Our curve is moving up. So what this is you're seeing around y equals 1, even on this phase portrait, on this number line, it's not like what you saw by 2, where the arrows are pointing at each other. That's being an attractor. It's not like just looking around a y value of 0 or a p value of 0 in that regard, where they're going away from each other. That's a repeller. This is very different. You're getting something that's known to be asymptotically semi-stable. So this is semi-stable at y equals 0. And this is because here we can say y is increasing, here y is increasing. The big question, I think, is what in the world would a family of solution curves look like? Well, once again, you could have by 1, you'd have tangent line slopes going towards 0. But if you had a curve that has to increase as you go left to right, well, you would probably picture it looking something like that, wouldn't you? If your y values are above 1 and you're increasing, it would look something like so. Your y is increasing when you're below 1 also. And you can think, how in the world could we get that? Well, it would be a different curve, wouldn't it? You know, a different curve on a different interval. It would look something like so. So this is being semi-stable. I think it's important to note, and we're going to see it sooner or later, that you could have one curve altogether. Obviously, the two curves that I drew right here, they're like separate curves. Could we get one function, perhaps, that would do it? This would fail the vertical line test. Could we get one function, possibly, that would represent this? And you've seen them already. I just wanted to quickly show you that if you drew something like this, both branches of this hyperbola that we have right here would be a rotated hyperbola, I should say. It's a rational function. As we're looking at this, you could see that below y equals 1, your curve is increasing, and above y equals 1, your curve is increasing. So that would be how you could get one function itself to obey that. So you might just be asked to draw a possible family of solution curves or a possible individual function, but this is what they would look like.